Hello and welcome. My name is Katrin Kirchhoff. I'm with Amazon, and in this next section of the tutorial, I'm going to talk about the analysis of self-supervised representations. So in the previous sections, we've seen how self-supervised speech models have really revolutionized a lot of different areas in speech processing. And they've shown pretty impressive performance on a whole range of different downstream tasks. So in this section, we'd like to go one step further and ask, can we gain deeper insights into how these models work, what makes them work, what information is encoded at different layers in a model, and how information encoding evolves over different layers. And also, how robust are models to different perturbations, different domains, or distributional shifts in training and test data? How does performance depend on data, data variety, data size, model size, and the particular network architecture or different objective functions that are used in pre-training? Also, do models generalize seamlessly across different languages, and can we use them in multilingual settings? And finally, we're going to look into the question whether there are pre-trained models that can generalize across different general audio processing tasks, not only speech-related tasks. So let's start by looking at information content at different layers in a pre-trained model. So what do networks actually learn at the different layers? So to answer that question, let's first of all take a look at the analysis methods that can be used in this context. Generally, we'd like to take a look at how similar embeddings are, either with each other's embeddings from different layers, or how similar they are with other continuously valued feature vectors, like, for instance, the input acoustic features, MFCCs, or log filter bank features. For that purpose, usually techniques like canonical correlation analysis are used, and that was already explained in one of the previous sections, so I'm not going to go into the details here. Cosine similarity is another popular technique. And beyond simply looking at the similarity between different acoustic and embedding vectors, we can also look at the relationship between the embedding vectors and discrete classes. For instance, phone classes, speaker classes, word identity. And that is typically done by clustering the continuous embedding vectors into a discrete space, and then computing the discrete mutual information between the clustered vectors and the class labels. Another popular task is probing. So this is the case where we train very simple downstream classifiers on representations from different layers. This could be a phone or a character classifier, or a word similarity predictor, or something related to speaker identification. The emphasis here is on simple downstream classifiers. We would typically like to keep that module very simple, not use too many parameters to avoid learning arbitrary input-output relationships that wouldn't tell us much about what linguistic information is contained at different layers. Another possible analysis method would be to use gradient analysis, where we look at the contributions of hidden layers to the gradient from a downstream objective function, all while keeping the parameters of the pre-trained model frozen, of course. So out of these different techniques, usually similarity techniques and probing tasks are the most popular ones. And with that, I would like to go into one particular example, which is the study by Pesad et al. From last year, where the different layers in the Wave2Vec 2.0 model were analyzed using different techniques. So first of all, similarity between the layer representations and filter bank features, which is shown here on the right-hand side. and also mutual information between embedding vectors and phone identity and word identity, and finally word discrimination tasks that were used as probing tasks. So the plot on the left-hand side here summarizes the insights from that study in a nutshell. The first thing that we see is that the early layers, probably up to layer 8 or 9, show the highest information about the input acoustic feature vectors. That then drops off, and then it increases again as we go deeper into the model and up to the higher level layers. So in other words, without any downstream fine-tuning, so this is just the basic pre-trained model, the model shows an autoencoder style behavior where the early and the late layers are more similar to the input. And that makes a lot of sense when you consider how the model is trained. The training process includes a reconstruction criterion. So it's not surprising that we get this autoencoder style behavior. The intermediate layers diverge more strongly from the input, and they're also the ones that show more information about the higher level categories like phones and words and word meaning. So that really peaks around layer 12, 13, 14, etc. And that has a lot of implication for how to use a model when it's used out of the box without any downstream fine-tuning. So rather than simply picking the topmost layer for any kind of downstream task that might benefit from lexical information, it may be beneficial to look at the intermediate layers. So another insight from the study was that this behavior of the top level layers changes after fine-tuning, again, not surprisingly. After fine-tuning on a downstream ASR task, even the higher level layers retain information about word identity and word similarity, and we don't see this drop-off that we saw in the basic model that had not been fine-tuned. There have also been a number of other studies that have taken a look at how other categories are encoded in pre-trained models, for instance, speaker identity, language information, accent information. And generally, we find that speaker identity is encoded at the lower layers, again, because this carries information about speakers' voices, vocal characteristics, which is more similar to acoustic features, whereas language or accent information does make use of phonetic information, phonotactics maybe, and that is encoded at the higher level layers in the model. It's also interesting to note that similar insights have been derived in other neighboring disciplines, especially in natural language processing. There have been a number of studies on analyzing different layers in pre-trained text-based models like BERT, for instance. And generally what people have found is that at the lower level layers, you also find very fine-grained information about parts of speech, for instance, morphology. And then as you move up to the higher level layers, more coarse-grained information about syntax and semantics can be found. There's also been a recent study from the vision community, again, on self-supervised transformer style models, where it was also shown that it was the intermediate layers that provided the most information about higher level classes. So generally with these kinds of models, we do seem to see the pattern that the lower level layers derive very basic fine-grained information, and the higher level layers introduce more abstractions and more categorical or semantic knowledge. So next, let's move on to the question of what aspects of a pre-training model are most important for the performance. Is it the training criterion? Is it the model architecture? Or is it maybe the directionality of the input data, whether the model is looking only into the past or also into the future? And this was studied in a paper from last year by Chang et al., where different models were analyzed with respect to the similarity of their representations. And models were distinguished by one of these criteria, by the training objective function, by the model architecture, or by the directionality of the input. The study also looked at the correlation of representations with downstream task accuracy, and altogether found that what matters most is the training criterion. Downstream accuracy is influenced by the training criterion first, followed by the directionality of the input, whether the model was uni versus bidirectional, and then finally the model architecture. So this is pretty important to keep in mind. Oftentimes, a lot of effort is spent on developing different architectures, but what really matters most is how the model is trained, what the objective function is. And this was also confirmed, I think, by a lot of other recent studies where modifications to training criteria have been introduced, Hubert, for instance, and Wavelem. So that still seems to be the most important ingredient to look at, whereas the specific architecture, for instance, is less important. So next, let's take a look at the effect of training data size. So there was a study by Kawakami et al. From 2020 that was one of the first to take a look at different training data sets that were used for pre-training self-supervised models. This was a CPC model that was trained either on LibreSpeech, which was 960 hours, versus 8,000 hours of data from multiple different sources. So in the table here, you can see the word error rates on LibreSpeech for, first of all, log filter bank features, the standard acoustic input features, and then CPC features trained from LibreSpeech or from the 8,000 hour corpus. So the pre-trained features perform better than the standard acoustic features, and features from the large model perform better than features from the smaller model. Not surprising, I might add. So we typically see this in all machine learning or deep learning scenarios. Training on large data sets typically works better. But what's at stake here is not just the data set size, it's also data diversity. Larger data sets typically imply higher data diversity. And in this case, in particular, the data set, the 8,000 hour data set, came from multiple different sources. So diversity counts, and we'll see some additional data points for that a little bit later on. The limits of large pre-trained speech models have not really been tested. There are a lot of new studies coming out that really scale up data sets to larger sizes. It's not quite as large yet as parallel models in the NLP community, I would say. And there's still some room to determine the precise relationship between data size, data diversity, and model size. So next we can take a look at how the model performance scales with the model size. How does the performance, and when I say performance here, I'm talking about the test loss, depend on the number of parameters in the model? Again, there's been a number of studies in NLP where the goal has been to come up with scaling laws for large language models. There was, for instance, a study by Kaplan et al., OpenAI in 2020. And that is a study that derived a power law for scaling of large language models that has this particular form, where L is the test loss and N is the number of parameters in the model. And sub C and alpha sub N are constants, and the particular value of those is not really important because they need to be fitted to the particular data sets that these models are trained on. But what was found is that the progression of the test loss in relation to the number of parameters in the model roughly follows a power law. That is not entirely uncontroversial. There have been follow-up studies that have proposed different scaling laws, but this is the one that was taken as the basis for the first study on self-supervised speech models that tried to derive a scaling law, which is a paper by Pu et al. From last year. So in this study, the Mockingjay model was used as a basis, and the authors varied the number of parameters in the model across 5 different orders of magnitude, from 10 to the 3 to 10 to the 7. The test loss that was used here was the reconstruction error for the predicted speech frames. And the authors did indeed find that performance scaled approximately according to a power law of this particular nature here. This can also be plotted here. Note that the axes here are both log, so it's a log-log plot, and then shows a linear relationship. But generally, the progression of the test loss approximately follows a power law as you scale up the size of the model. There is a bit of a caveat here. The authors found that this is not necessarily true for the performance on downstream tasks. So if you take a look at the loss on any kind of downstream tasks, you're not necessarily going to see that relationship. And the missing variable here, or the other ingredient, is of course the data size. It is pretty important to also take data into account as you scale up a model. Typically, as you enlarge the model, you'll also want to scale up the amount of data that you train it on. And again, this is probably a relationship that can be analyzed in more detail. The take-home message here is that scaling up of model size and scaling up of data size should really go hand in hand. So as the next topic in our analysis, let's take a look at robustness to domain shifts or distribution shifts more generally. So how do self-supervised representations fare when faced with a mismatch in training and test conditions? And especially, how do they compare against standard acoustic features in that context? So in that context, I'd like to again cite the study by Kawakami et al. From 2020, where this was measured on different corpora: Wall Street Journal, LibriSpeech, TEDLium, and Switchboard, for, first of all, the standard acoustic log filter bank features, and then different CPC models trained on LibriSpeech or on the 8,000-hour multi-source corpus. And what we see is that performance is much better for the pre-trained features across different domains. And again, the larger model is more robust to different domain shifts than the smaller model that was trained on LibriSpeech only. So this is not surprising. One thing to keep in mind is that the differences between different corpora here reside at different levels. So it's not just difference in the acoustics, there are also differences in the lexical domains, in speaking styles and different accents. And it's of course difficult to tease apart what precisely is the biggest contributor to domain shift and how different models or different representations react to that. But generally, the basic conclusion again holds: representations from self-supervised models are more robust to domain mismatch, and models pre-trained on larger data and more diverse data sets, again, fare better than smaller models. The question of robustness to distribution shift was also investigated in another study by Su et al. From last year, where pre-training and testing on different corpora was analyzed in a bit more detail. There were 6 different corpora or domains. So the left-hand column here shows the corpora that the model was pre-trained on, and TD stands for Ted Liam, LS is LibriSpeech, SF is Switchboard Fisher. And then we have testing on Wall Street Journal, WS, CV stands for Common Voice, BP is Vox Populi, and we see the word error rate across these different out-of-domain corpora. So we see that pre-training on multiple domains is preferable. We typically see better performance when we combine more corpora during the pre-training stage, and the best results are obtained by all 3 different pre-training corpora. And one other insight that the study found was that pre-training on domain match data is typically best, but even out-of-domain data helps in pre-training in narrowing the gap to supervised models. So in other words, when you only have mismatched data, it still helps to include that in pre-training and to combine different data sources. Of course, when matched data is available, that is even more helpful. So then let's take a look at how models generalize across different languages. So do self-supervised representations generalize across languages out of the box? Can we use them as a basis, for instance, for training models for low resource languages where we don't have a lot of in-domain or in-language data? What does that look like? So again, referring back to the Kawakami et al. Study, there were representations from a self-trained CPC model that were analyzed and compared against standard acoustic features for different languages. The model was pre-trained on mixed speech data from 29 different languages and then applied to an ASR task on 22 different test languages. And this also included languages that were not included in the pre-training data, like Wolof, for instance. So the bar chart here shows the relative improvement over log-mel filter bank features on different languages. These are the different language codes. And we generally find solid improvements over log-mel filter bank features across the board, even for languages that were not represented in the pre-training data. Another question we could ask is, well, how does multilingual training perform in the case where we actually have quite a bit of monolingual training data? Do we still see any gains from multilingual pre-training, even when the monolingual data is sufficient for pre-training a model? That was investigated in a paper by Conoe et al. From 2020, where monolingual pre-training was compared against multilingual pre-training, and that was investigated on up to 53 different languages. So the largest model that was used, XLSR 53, that's shown in the bottom row here, that of course showed the best performance across the board. But comparing monolingual models and even models that were trained on just a fairly small set of different languages, 10 languages in this case, showed that the multilingual models performed better and outperformed the monolingual models. So again, this points to the data diversity effect. Incorporating more different data sources in pre-training from different languages, even when it's a fairly small set, is helpful. So diversity is key. So as a final topic in this section, let's take a look at whether there is any kind of pre-trained representation that can generalize not only to different speech tasks, but also to more general audio tasks. So can self-supervised representations generalize more broadly, and can they function as general acoustic feature extractors similar to the human ear. There was a challenge workshop at NeurIPS last year that took a look at this question that included 19 downstream tasks as challenge tasks. 5 of these tasks were open to participants and 14 were blind, meaning that participants didn't know what kind of audio classification task their model was eventually going to run on. And these included both speech-related tasks like emotion recognition and ASR, and general non-speech audio classification tasks like environmental sound classification or music genre classification, for example. The downstream classifiers for these tasks were fixed. So all that varied was the input pre-trained representation, which needed to be used for all tasks. Participants submitted 29 different models, and it would really go too far to present the full matrix of results of all 29 models across all 19 tasks here. So I'm just going to give you the gist and the outcome from this exercise. So the result was that there is no single representation that stood out as being the best and as generalizing robustly across all different tasks. The representations that were pre-trained primarily on speech data performed reasonably well on related tasks like emotion detection or language identification, for example, but not on others. And some tasks generally saw very poor performance. One example of that was a vocal imitation task where human speakers were asked to imitate different environmental sounds. So there's usually no standard data we have for pre-training for those kinds of tasks. So these are still very much edge cases and out of the capability of the current pre-trained models that we typically work with. So as of yet, there's no self-supervised model for general purpose audio processing. So that is still open for investigation, open for research, and there is still a long way to go. So this concludes my section of the tutorial. I hope you found some good pointers for further reading and further ideas. Thank you for attending our tutorial, and on to the next speaker.